Many of them are online.
Okay.
So, hi everyone, very welcome to the talk. And it's our pleasure to have Navid. And Navid is a PhD student from the University of Toronto, and he works on data structure a lot, especially database systems, and focusing on randomized and sketching data structures. He also optimized his data structures to leverage the power and speed of modern hardware to the fullest matching the lightning fast. Well, so let's start.
All right. Thank you very much for the kind introduction. I'm Navid. Nice to meet you all. Yeah, today I'm very excited to be talking about the work I've been doing thus far in my PhD. This is joint work with some colleagues from the KTH University in Sweden and BARC, which is actually where I first was acquainted with Hanji during a visit to Copenhagen. So yeah, I'm going to be talking about specifically succinct data structures with a beyond worst case flavor. Okay. Oh. All right. So as I'm sure you all know, nowadays we're in the age of big data, right? And our data is growing by the second. We're getting more and more machines connected to our clouds. We're getting more data, and we have to analyze this data. And specifically, we have to analyze it to answer statistical queries. So stuff like you want to see if a key exists in your data. You want to see if a range of keys exist. You want to count keys, and so on. But the core issue is our data is so big that, well, we can't really fit it in memory to do this analysis. So what people usually do instead is they create these randomized data structures, well, usually randomized, to basically compress that huge amount of data that we have. And, well, this compressed version is going to allow us to compute our statistics in an approximate fashion. But, because this data structure is small, now I can fit it in memory. But the core shortcomings of the sketching data structures that we have nowadays are that, well, they're all either slow or they give you the practical ones, they give you some sort of ad hoc accuracy. There's not really a guarantee on approximation errors or anything. And they're designed with this one size fits all mentality in the sense that, well, they're designed for only the worst case. And, well, this is in some sense not really good for people working in practice, because a lot of the time in practice you have nice properties in your data that would actually allow you to do better than the worst case in most of the time. So my work is mostly focused on, well, making these sketches fast in practice, giving you provable accuracy guarantees, and generalizing that one size fit all worst case mentality to basically tailor your data structures to your workloads. So whenever there's a pattern in your workload that makes the problem easier, we're going to be able to leverage that and either give you like better speed or better memory. But still, I'm going to also be able to guarantee the same worst case guarantees that we're all used to and love, while still giving you that added benefit. Okay. So this is in the sense that we're going beyond the worst case. All right, so today I'm going to be talking about two problems that we've been working on. The first one is range filtering, and the second one is frequency estimation. For range filtering, I'm going to present our work from VLDB 25 called Diva. And for frequency estimation, I'm going to talk about our work on Sublime, which is being presented in SIGMOD 26 this year. I was fortunate enough to get a best paper award for Diva, so I'm kind of excited to be tooting my own horn here. But yeah, let me jump right into range filtering. So let me start by describing what a filter is. A filter, as I'm sure you all know, is a compact probabilistic data structure that approximates a set of keys. You can give the filter a key X and ask if that key exists in your set or not. Okay. Because filters are compact, again, they're like sketches, so they oftentimes fit in memory, and they approximate those big data sets that we have stored on disk. Okay. If the key that we give the filter actually exists in the data set, the filter is guaranteed to return a true positive to us, telling us that, well, we have to go fetch the key from disk. And if the key doesn't exist, well, most probably the filter is going to tell us it doesn't exist. But with some small probability epsilon, it might actually return a false positive to us. And, well, if we get a true negative, we can avoid accessing disk, but if we get a false positive, we might have to do a redundant access. And well, that probability epsilon is actually a tunable parameter of the filter, which you can reduce by giving the filter more memory. But because filters are, guaranteed to give you true negatives most of the time, they're used in all of computer science to basically avoid accessing disk and avoid doing network hops. So they speed up things significantly in exchange for a little bit of a memory overhead. Okay. So filters are great, we love them, but they have one core limitation, and that is they only support point queries. So you can only give them a single key and ask if it exists or not. The natural question, especially in database systems, is what if I want to basically analyze a range? What if I have a range of keys and I want to know if that range has any key included within it? So something like this. I give the filter 2 keys from A to B, and I want to see if any key between A and B exists in my set. So I still want the same sort of semantics as before. I want a small false positive rate, and I want true negatives most of the time. This thing would be a range filter. And the core question is, how do we implement one? Does the setup make sense until now? Okay, cool. All right, so a sort of strawman solution to this problem is to basically use a point filter to do range filtering. So you could start with something like a Bloom filter. And the idea would be to basically take your range and issue a subquery for every single key that you have in your range. Now, the way that you would aggregate these results is if all of those subqueries return negative, you know that the range is empty. But if at least one of them is a positive, then the overall outcome becomes a positive. Now, this approach works, but it has its problems, as I'm sure you know. The first one is that it's terribly slow. If your range is really, really big, then you're issuing many, many subqueries to the underlying filter, and that's going to slow things down significantly. This multitude of subqueries that we're also issuing is actually going to increase the false positive rate of our filter. To see this, well, suppose we're starting with a false positive rate of epsilon with our filter, and we're issuing R subqueries. Then by a union bound, we can basically show that the false positive rate is going to be R times higher than what we started out with. Now, so this actually makes the filter useless when you have long range queries because it's just going to return positive every single time. Now, granted, you can give the filter more memory to reduce that epsilon and compensate for the R, but that actually requires us to know what the maximum range query length is up front. And that's not really something that people know in practice. The third problem is a bit more severe than that. And it's basically saying that this entire approach of issuing a subquery for every key breaks down the moment you have an infinite universe. So let's say if we're working with string keys, then any range we pick, let's say from A to B, is going to have infinitely many keys inside of it. So you can't even begin to enumerate them and ask the filter for every single one. So we're kind of stuck here. Okay. So to summarize, we basically have 4 problems here. We have a high query cost, we have a high false positive rate, and we're stuck with bounded queries and fixed length keys. Ideally, what we want to do is we want to get a query cost that's close to constant time. We want to get a false positive rate that looks like epsilon. We want to support variable length queries and variable length keys. In addition to that, this is sort of like a new requirement for filters nowadays. We want to support dynamic operations as well. So we want to be able to maintain our filter as our data set is being modified. So with inserts, deletes, updates, so on. Okay. So range filtering has been a pretty big research topic in the past decade. We've had both theory papers and practical papers on it. But what's interesting is if we look at the practical papers, we see that basically only 2 give you fast queries. Only 4 give you some sort of a false positive rate guarantee. Only 3 give you variable length queries. Only 1 actually supports variable length keys. And only 1, which is our work from 2025 actually, is dynamic. This is just me trying to say that none of these previous filters achieve these 5 goals that I mentioned simultaneously. This is where we come in and design Diva, which is the first range filter to give you these 5 requirements at the same time. Okay. All right, so let's get into how Diva works. The core sort of innovation in Diva is to basically dump the core, the most widely used primitive in filtering, which is hashing. Okay, so we're just going to dump hashing. And what we're going to do is we're going to store our keys lexicographically from A to Z. So what this is going to allow us to do is, well, given a query, we just have to find the successor of the left endpoint. Again, to remind you, the successor is the smallest key that is bigger than the left endpoint. Well, when we find the successor, we just have to compare it to the right endpoint. And if it's, well, smaller than the right endpoint, then the range is non-empty. And if it's bigger than the right endpoint, then the range is empty. So this is going to be our query plan. And the only thing that we need really to support this query plan is to support fast successor search over a compressed representation of our keys. So the way Diva achieves that is, and well, compresses the data set, is by using the data set's distribution. So here I'm showing you the cumulative distribution function of our data set, or the CDF. You can think of this as basically the slopey parts showing the dense regions of the key space and the flat parts representing the sparse regions. And what Diva does is it's going to sample every 1,000th key from this data set, and it's going to connect these samples with straight lines. So we're going to get this piecewise linear approximation to our underlying CDF. So yeah, the core observation here is because the actual CDF looks like, in between two samples, looks like the line connecting two samples, and because lines in CDF language correspond to uniform distributions, we can show that the keys in between two samples are approximately uniformly distributed, more or less. This gives them a sort of inherent randomness, which makes them look like hashes, even though it's not really a hash. They have this randomness that we can leverage to do things like traditional filters. So this is the core property that we're going to leverage to do range filtering. Does that make sense? If at any point there is any question, please stop me. I would love to answer. Okay, so let's see how we can use this property to do range filtering. So the first thing we're going to do is we're going to store our samples in a tree. So this is going to be something like a binary tree. And you can this tree is going to be super small because I'm only storing every 1,000th key of my data set. So it's only going to be 0.1% of the data size, which in practical terms, with the data sets people have usually, this is going to fit in the CPU cache. So it's going to be really fast to access, and it's, well, negligible in size. So the core question remaining is, how do we handle the 1,000 keys we have in between any two samples? The way we're going to do this is by designing these data structures called infix stores. So an infix store is a order-preserving hash table of compressed keys. That's a bit of a strange name. It's a bit of a mouthful. So let's dissect that and see what that means. An infix store at its core basically takes the keys it's working with, and it compresses them by removing their longest common prefix first. Cool. Perhaps I should. Okay, yeah, cool. So by removing this longest common prefix, we're not really losing any information because that prefix is already stored in the tree that we had before. Okay, so we remove that. Then what an infix store does is it removes a suffix from each key to homogenize their lengths. So here is actually where we do lose some information because we're not going to be storing these suffixes anywhere in the data structure. But it allows us to convert our variable length keys into fixed length representations that are easy to work with. So what we end up with from each key are patches of bits that we've taken from the middle of each key. So they're not prefixes, they're not suffixes, but they're something like an infix. Because these infixes are patches of bits that we took from the keys themselves, they inherit, well, they first of all maintain the original ordering of the keys because they're from the keys themselves. And they inherit the same uniformity that we argued exists for the keys in between two samples. Okay. So this gives them a sort of fingerprint type property. They're like a hash, a small digest of the key that's uniform. So this is going to be basically prime real estate to use a hash table. We're going to store these guys in a hash table. Well, it's going to be something like a compact hash table. I'm going to get into how that works in a second. The way it's going to go is we're going to first divide our infixes into addresses and fingerprints. These addresses, well, you can think of the addresses as being 10 bits long because we want to store 1,000 keys in our infix store. So we have to have 1,000 slots we have to be able to address. And the fingerprints you can think of as being log of 1 over epsilon bits long to give you a false positive rate of epsilon. Okay, so with that setup, let's see how our compact hash table is actually going to work with a running example. Here I'm going to insert a bunch of infixes in increasing order. So this is the minimum infix that I'm going to insert in my hash table. The way that I'm going to do this is in my hash table, I'm going to have a occupied bitmap. This occupied bitmap is basically going to store which addresses have I seen thus far in my infixes. So in the first infix, I have an address of 0. So the way I record it is I go to the 0th bit and I set it to 1. Then, well, now I've basically recorded my address for that infix. Then I just have to store the fingerprint itself somewhere in my data structure. So I allocate an array of slots and I store that fingerprint in the first empty slot that I find. Then I continue doing something similar. So if I get my next infix, its address could be something bigger than what I had before. So this is going to map to the second bit in my occupied bitmap. I'm going to set that to 1, and I'm going to store the fingerprint in the next empty slot. Again, if I get a third infix, and that shares the same address, well, now that bit is already 1, so I leave that as is, and I store the fingerprint in the next empty slot like that. So basically what's happening here is infixes that have the same addresses are going to be stored in contiguous slots in my hash table. So these contiguous slots, I'm going to call runs from now on. Mm-hmm. And I'm going to denote them with this just to get rid of the color.
Like midday, 12.
Oh, yeah? Did anyone have a question? Nope? Okay. All right, so if I continue inserting keys like so, I'm going to fill up my array of slots and my occupied bitmap with a bunch of data, right? And I'm going to get this run structure right here. In principle, this is already enough this is almost enough to get, well, basically reconstruct every single infix that I have in my hash table. The only thing that sorry. So each run actually corresponds to exactly one bit in my occupied bitmap. Right? This is because each occupied bitmap is each address map to 1 bit in the occupied bitmap, and I'm storing the corresponding fingerprints consecutively in these slots. So
How do you record the boundary of the runs?
Yeah, I'm gonna get to that. This is almost enough to decode everything, but that's a problem. Yes, exactly. We don't know where the boundaries of the runs are. We have to delimit them. So the way I do that is I basically add an extra bitmap, the run-ins bitmap. Then this thing just has a 1 where in the position corresponding to every slot that is the end of a run. Okay. So now this thing is fully decodable. And you can reconstruct your infixes by just finding the address and reading the corresponding run and concatenating the fingerprints with the addresses. Okay. So yeah, now let's talk about accessing this thing. This structure has a really nice property in the sense that the ones that we have in our occupied bitmap have matching corresponding ones in the run-ins bitmap. So you have this type of structure right here. This is and the next nice property that we have is that these matching ones have equal rank. So what I mean by this, what I mean is the first one, or the first existing address in the occupied bitmap corresponds to exactly 1 run in the run-ins bitmap, right? And that run has 1 bit set to 1 in the run-ins bitmap. And this one is actually also the first 1 bit in that bitmap. Okay? The same with this one. The second one in the occupied bitmap corresponds to the second one in the run-ins bitmap, and so on. So what this allows us to do is we can basically traverse this mapping, this correspondence, using rank and select primitives. These primitives are really, really common and core to succinct data structure design. And basically what they do is, for rank, you give it a bitmap B and an index I, and the return value is the number of 1 bits you see before the ith bit in that bitmap. So it's basically like a partial sum you take from the bitmap. And select is sort of the inverse. You give it a bitmap and you give it the number of 1 bits you want to skip, and it gives you the position of the ith one bit in the bitmap B. So I'm going to be able to use these guys to traverse this by simply finding the rank of this guy in the occupies bitmap and doing select on this run-ins bitmap to go exact with the result of that rank operation to go exactly to where that corresponding one is. Does that make sense?
So rank and select, you only need to focus on the second table, the run-ins, not the
Right. I have to first do a rank on occupied to give me like the rank that I have to select for in the run-ins bitmap. So let's say I have an address of 3, and I want to go to its corresponding run-in. I have to first do rank here. That's going to count these two guys. It's going to be 2. Then I plug that in for select on this, and it's going to give me the position of it.
Sorry.
Yes, yes. Yeah. And the nice thing about these operations is that, well, most kind of recently, we've had these super nice efficient CPU instructions that we can use to implement these things. And yeah, basically it's extremely practical. We can make very fast implementations for these. Okay. So all in all, what we ended up with is a order preserving hash table with constant access time. So the reason why it's order preserving is because this hash table is storing the infixes, and the infixes preserve the original ordering of the keys. And the reason why it's sort of like a hash table that gives you constant access time is because those infixes were uniformly random, approximately. So those runs that we had were going to have 1 to 2 infixes, 1 to 2 fingerprints inside of them in expectation. Okay. Does that make sense?
For example, like the last question, if you count the rank,
Mhm.
can you do this in the constant time? Because I think you understand.
Yes, doing rank is actually possible in constant time. Yeah, and at least in the static setting, it is possible in the constant time. So rank is like both are doable in constant time in the static setting. In the dynamic setting, you have to pay logarithmic time, but that's still constant time in our setting because each infix store had 1,000 keys inside of it. So, because that 1,000 is like a constant number, that turns out to be constant time. Does that make sense?
So where is the login dimension if you cannot?
Oh, yeah, sorry. So in this case, so the question is where in the dynamic setting, where does the log n show up? The n in the dynamic setting is basically just the number of guys I have in my infix store. So it's technically log of 1,000.
Oh,
So even though it's logarithmic in the size of the bitmap itself is constant. So it turns out to be constant. Okay. Any other questions?
Hey, Navi, I'm just curious, are you aware of the Succinct data structure for range mean, which takes a bit of MBs that can support range mean queries on O1 time?
Sorry, could you repeat the question?
Are you aware of the Succinct data structure for range mean?
Of range min?
Yeah, range mean, which takes only just a bit of MBs for storage and then can support a constant time for queries.
Right, yeah. I've heard of this, yes.
Yeah, basically here you pick every 1,000 keys, so you pick a sample, right? So basically overall the space consumption it is all still bounded by big of n, right? Just one over 1,000 still a constant. So theoretically it is the same, right? And the range mean can also support the precise queries.
So the core difference here, I think, is the range min data structure that you're referencing has a asymptotic space complexity. Here, what we care about is actually the exact space complexity. What I want to get in the end is something like log of 1 over epsilon bits per key. I basically I care about that constant factor that we're hiding in the asymptotics. Does that make sense?
So if you store the overall data set, it takes you to n over log u bits, right? U it is the universe size.
Yes.
Okay, so are you aiming to achieve n log u bits for your data structure?
I'm aiming to achieve n log of 1 over epsilon. I want to make it independent of the universe size.
Oh, okay. Okay. if you achieve a log, okay, n log 1 over epsilon, so naively, actually, you can still also apply for sampling for the subsampling on the universe, right? Every epsilon, epsilon times u, then you pick a sample, and then you still apply the same trick here. So
Yes, that is doable. But the issue is if you do that, then you might lose some accuracy in terms of range queries. The semantics of range queries is going to kind of get muddied in some sense. Does that make sense?
yeah, there are some details that need to be fixed. Yeah, makes sense. Okay, good, thanks.
No problem. Any other questions from online? Okay, cool. All right, so to recap, we have now a data structure which is a cache tree, basically, with a bunch of infix stores. The cache tree we're going to implement using a YFast try, which is a cute data structure from the 80s, which you can think of as basically giving you successor search with log of L time, where L is the length of the key you're searching for. This is going to be much faster than using a standard binary search tree, which would have given you a logarithmic time complexity in the number of keys you're storing. And the infix stores, we just established that they were constant time. So all in all, we have a runtime of O of log L for our data structure. So the core question remaining is, how do we check if a range is empty? So let's say we get a query. The first thing we want to do is we check our try to see if there's any sample included within the range. If there is one, then the answer is a true positive. Again, it's a true positive because I'm storing the actual keys in my try. So the more interesting case is when my query is so small, in fact, that it's included within a singular infix store. It doesn't. Yeah, sorry. There was a. No? Okay. Yeah, so the interesting case is when my query is so small that it's included within a single infix store. So it doesn't have any samples in it. In this case, the idea is to basically take the query endpoints and compress them in the same way that we compress the keys within that infix store. This is going to give us a range query over infixes now, which we can handle by basically scanning the infix store, scanning the hash table that we have. Here as well, we get a true positive if we find an infix that is strictly in between the query endpoints. This is because the infixes maintain the original ordering of the keys. So if we see something that's strictly in between, that corresponds to a key that is strictly in between the endpoints of our query. So we actually only get false positives whenever our query endpoints happen to exactly match what we're storing for an existing key. And the probability of this happening is, well, 2 to the negative f, where f is the length of the fingerprint. Does that make sense? Okay. Now, this guarantee is fun. We like it, but it's a bit different from the guarantees that we're used to seeing. And the guarantees that we're used to seeing are for the worst case. This is where we go beyond the worst case in some sense, and we get a semi-robust guarantee. So basically, this guarantee holds for smooth distributions. So stuff like numeric data we're really happy with, but it holds less well for distributions that are more jagged. And we have actually observed this for natural language data in our experiments. But we have also seen that you can use entropy encoding to compress your original data set. That compression operation is gonna get rid of those jumps in your distribution and sort of implicitly smooth it out. This is gonna help Diva, handle these jagged distributions a bit better and basically work its magic. Yes?
One of the things you were talking about earlier on with regards to smooth distributions and properties, it seems to be advantageous to have essentially differentiated regions, sharpness versus shallowness.
Yes.
But if you're doing an entropy encoding, my understanding would be that everything's going to smooth out to some level. Or am I kind of overthinking that? Like, is there still going to be the kind of differentiation between sharpness and shallowness?
I'm not entirely sure I understood the sharpness versus shallowness thing.
Yeah.
Could you repeat that?
I was thinking about the fact that, like, when you're originally describing the useful properties of distributions, you were talking about like differentiated steepness in the distribution of having advantage of so back into sharpness versus shallowness.
Yeah. No, it makes sense. So So the differentiation thing is, you're right. I think what's going on underneath the hood is the best type of differentiation you can hope for is basically a uniform distribution. So in some sense, you want to make your distribution. We don't really care about whether it's, well, we do care about if it's smooth, because then with sampling you can get like local uniformity. But what we really ideally want is to make this entire thing a straight line. Compression gets that closer to that.
Yeah, thank you.
No problem. Okay, so that's it for range filtering. Let me get into the new work we have on frequency estimation. So the setting here is a bit different. Here we have a stream of keys. These keys could be, in any order, and they could repeat. And the idea is we want to compute statistics over the string. So things like the max, the min, the max, the mean, and more complicated things like cardinalities, quantiles, and so on. Okay. Well, we have streams all over the place in practice. For network traffic, we have streams of packets that we want to analyze. For social media trends, we have streams of clicks of what user clicked on which post we want to analyze. And for system performance analysis, we have events that happen in our, let's say, distributed system. Some server sent like a message to some other server, or some server crashed. These are events that you want to analyze. But the issue is, in reality, these streams that we have are growing over time. They're getting bigger and bigger at a really, really high speed, which actually makes these streams way too large to store in any sort of storage, even on disk. So that means we can't really store these guys and compute statistics by doing a single pass over, by doing multiple passes over them potentially in an offline fashion. So what people usually do is they incrementally maintain the statistics that they care about. So for max, min, and mean, this is trivial. You just have to store like one value and update that as keys come in. But for other statistics, such as cardinalities or let's say quantiles, this is a bit more complicated, and you have to be a bit more careful about what you maintain. The statistic that we're interested in today is frequency. So you want to count for any given key how many times it occurs in the stream. Well, of course, you can use a standard dictionary to do this. You can store your keys in a hash table and map them to their counts and just update this. But the issue with doing this is that this is actually very expensive in terms of memory. You have to store every single unique key, and you have to store also a unique counter for every single unique key. So this is, and because the stream is like huge and we have many, many unique keys, this is not going to be something that people are really interested in doing. So what people instead do is they use these things called frequency estimation sketches. The idea here is we don't want to store full keys anymore, which is, well, nice in terms of memory, because it's going to be much, much better in terms of space. But the issue is, well, we get better memory in exchange for approximating the actual counts. We no longer get exact counts. Okay. These things have applications all over the place. They are used to approximate distributions, because having the counts is basically the same as having the distribution of your stream. They're used in covariance estimation in machine learning, and they're also used in things like attack detection. So let's say if you have like a network of servers and you want to see if there's like a DDoS against one server that you care about, you basically have to count how many packets are going towards that server with some space-efficient data structure like a sketch. And yeah, that's going to give you an indication of some sort of attack is happening. Okay. The most famous and the most commonly used frequency estimation sketch is the count-min sketch. So I'm going to go over that and give you an idea of its shortcomings and how it works. Okay, so the core design element in a count-min sketch is basically just a counter array. We initialize this guy to 0, and we use it to handle our stream of keys. Whenever we get a key in our stream, a new insertion, we just hash that key to a random counter in our counter array, and we increment that counter by 1. Okay. If I get another key, the same thing is going to happen. I'm going to hash it. I'm going to increment the counter. And if I get the same key twice, I'm going to because I'm using hashing, I'm going to increment the same counter once more. Okay. So in some sense, these counters are counting how many times I've seen these keys in my stream. But of course, because I'm using hashing, I might see a key that accidentally maps to the same counter. right? And this is going to be basically a hash collision event. And if later on I want to query a key, the procedure is to basically just rehash the key, go to the counter and read its value. But because of hash collisions, I'm going to get inflated estimates. So this is where the space saving versus approximation trade-off comes in. Okay. And of course, deletes work in the same way. If you delete some key, you just go hash it, go to the counter and decrement it. Very simple. Okay. So this data structure is very simple and it's very cute. And you can actually show that if you have a stream of length n and you have W counters in your counter array, you have a expected error, estimation error for any key of n over W. And the reasoning for this is, well, any key you have in your stream has only a probability of 1 over W mapping to the same counter that you've mapped to. So the amount of inflation that you see is n over W. People use Markov's inequality on this thing to prove a probability bound on how much the error actually exceeds this threshold, how often it exceeds this threshold. And well, you guys know this usually as the confidence bound. And people also use multiple independent arrays with independent hash functions to sort of repeat this experiment and get better estimates to improve confidence. But because the techniques that we're going to talk about today and the problems are independent of this multiple array setup, we're just going to focus on the case where we have a single array and keep it simple. All right, so that's the Kalman sketch. It has a bunch of problems, of course. Otherwise, I wouldn't be here talking about it. Okay, the first problem is that it is actually, it wastes a lot of memory when you have skew in your string. So what I mean by this, well, a lot of the time in practice, the counts that we care about in our streams and the streams themselves are skewed. So let's say if you have like if you want to track the popularity of websites in a search engine, people have studied this thing for years and years. We've observed a Zipf-like distribution for how many times people click on a given link based on its ranking in the search result page. So the first few links that show up on a web page are being clicked way more than everything else in the web page. But it's everything else in the web page in the search results combined is like a heavy tail. So these guys are also non-negligible. So yeah, we have skew basically everywhere, practice in pretty much every single domain. But the problem with skew is if we use a Kalman sketch to track these types of streams with that sort of skew, some of our counters are going to be much bigger in value than, well, pretty much every single other counter we have in our array. Now, because the Kalman sketch uses uniformly sized counters, you have to have, well, each counter has to be big enough to store the maximum count in your stream. And so in binary, what this would look like, well, here I'm showing you the lower order bits on the left and the higher order bits on the right. What this would look like is, well, that big counter is going to be used fully, but everything else is going to have redundant leading zeros, which are basically left unused. They're not really helping you with anything in terms of estimation. So we're wasting substantial memory on storing those leading zeros. And well, ideally, we would just like to get rid of those leading zeros and store each counter. Well, and we want each counter to be just long enough to store its value. Okay. So that's the first problem. The second one is actually, well, if you use a Kalman sketch, you're going to get deteriorating accuracy as the stream grows. So this is, to see this, recall that the Kalman sketch used a fixed number of counters of, let's say, W. And with a stream of length n, we got an error of n over W. So this error bound increases linearly with the stream's length. So as the stream becomes longer and longer, your error is going to get worse and worse over time. So if you're using this type of sketch to, power decision making in a system, as time goes on, your decision making is going to get worse and worse, and the quality of service is going to go down. So. And what's unfortunate about this setting is you can't really control the error by rescanning the stream and constructing a larger sketch. This is because, if you recall, these streams are way too large to store, so we can't rescan it anyway. Okay, so the goal here is we want to keep not only memory modest, but also the error modest over time for streams of arbitrary length. Does that make sense? Okay. So we have two problems to speak of. We have the skew problem and the unbounded streams problem. For the skew problem, people have, well, explored many different techniques to resolve it. We have counter sharing, counter merging, hybrid methods, compression-based methods, and so on. These all get rid of those leading zeros in one way or another. But the issue is they're all inaccurate with unbounded streams. So if your stream is like growing over time, you're going to get worse and worse errors beyond what you would expect from a standard Kalman sketch using those techniques. They also remove the ability to support deletes, and they're mostly slow. So yeah, we don't like that. For unbounded streams, the situation is sort of interesting. This is apparently an entirely new problem. This hasn't been studied before at all. So it's going to be fun to see what we can do in that space. And so we have 4 goals in total. We want to support skewed streams with better memory. We want to support unbounded streams with better errors. We want to do these 2 things while supporting deletes and also being fast. Okay. So yeah, we designed the first sort of framework that allows you to generalize existing frequency estimation sketches to do those 4 things at the same time, called Sublime. So Sublime uses 2 core techniques, one to address each one of those problems. The first technique is to use variable length counters for skew. And the second one is to expand the number of counters we have in our array as the stream grows. We're going to do so carefully to make sure that memory doesn't blow up. Okay, so let's get into how we handle skew. So when we apply Sublime to the Kalman sketch to generalize it and improve its memory footprint, basically what we're going to do is we're going to take our counter array and we're going to split it into chunks. Each one of these chunks is going to be encoded within a cache line in our memory. And within that cache line, what we're going to do is we're going to store our counters up front with short counters we like to call stubs. So we can think of these as 4-bit or 3-bit counters. So we continue inserting and deleting keys from these stubs until we get a overflow. So because they're short counters, overflows are bound to happen. Whenever an overflow happens, what we do is we employ an extra overflows bitmap, which tells us which counter in this stub array, which stub has overflowed. Then with that overflows bitmap, we know that we have extra data to fetch from somewhere. So what we do is we store those high overflowing bits in extensions, variable length extensions, to be exact. Those extensions we're going to store in an extension pool at the end of the chunk. So yeah, so basically when we try to read a counter, we first read its stub, check if it has overflowed. Then if it has overflowed, we access the extension pool. The extension pool, the extensions themselves are formed from 2-bit fragments. Each one of those fragments has a delimiter at the end, which is basically just a 1-1 sequence. And we're going to use the other 3 combinations of 2 bits to represent the overflowing bits in base 3. So 0, 0 is going to be 0, 1, 0 is going to be 1, and 0, 1 is going to be 2. Okay, so for example, if I have this sequence encoding my higher order bits, this is the less significant digit, and this is the more significant digit. And that's going to give me the expression of, this guy is 2, so 2 times 3 to the 0, and this guy's 1, so 1 times 3 to the 1 gives me 5 for the higher order bits. And given this, because I know the lower order bits in my stub were 15, I get the counter value of 5 times 16 plus the 15, which gives me the 95 value of my counter. Does that make sense? Okay, so this is how I reconstruct counters, the counter values from the stubs and the extensions. And of course, if I get more insertions, I do the same thing. When I get an overflow, I set an overflow bit and a 1 bit in my overflows bitmap, and I store an extension, a new extension in my extension pool. What I do here in the extension pool is I maintain the extensions in the same order as the stubs. So this means if I want to access this counter's extension, I just have to skip over the extensions of all of the other overflowing counters to its left. So this guy specifically. So yeah, that gives me access to its extension. And based on that, I can tell well, its value. Now you can loop over the extensions to basically determine where these guys are stored in the extension pool. But that's actually going to be really expensive in terms of CPU in practice. Because, well, now you have like an if statement that you're constantly checking, and the if statement is data dependent. So it might sometimes evaluate to true, it might sometimes evaluate to false. That's going to confuse the heck out of the CPU's branch predictor, which is going to slow things down significantly. So instead of doing that, we're actually going to speed up this process using rank and select. So again, to remind you, rank took a bitmap and an index and counted the number of ones before that index in the bitmap. And select took a bitmap and a position, or I, and told you the position of the ith bit in that bitmap. Okay. So the way we're going to use these guys to locate the corresponding extension of a counter is, well, let's say, as an example, I want to find this counter's extension, right? The fourth counter, the fourth stub. What I do is I first compute the rank of this guy among the overflowing counters. Since, well, this guy is the third in the third position, and I have only one before it, the rank is going to be 1. This tells me that I have to skip over one extension in the extension pool. Okay. So the way I do this is by applying select. And the way that's going to go is, well, I'm going to look at the extension pool. This by itself doesn't really give me any way to apply select on its own. So I have to do some processing to turn this into a format that I can use select on. So the way I would do that is I'm going to copy this extension pool. I'm going to shift it to the right, and I'm going to AND it with the original extension pool. So what I'm going to get in the end is a bitmap that looks like this. The core feature of this bitmap is, well, this has a 1 for every 1 I originally had in the extension pool. So the delimiters themselves are going to have a 1 there, but I might also have some pesky ones, which are formed by 2 1s from different fragments of my extensions. But the core observation is those unwanted ones are at odd positions in my in this bitmap. So the ones that I care about are only at the even positions. So I just have to mask this thing out. And this, what I end up with is a delimiters bitmap, which has a 1 exactly for every single delimiter that I have in my extension pool. This thing is now basically ready to apply select to. So I just take the output of my rank, I plug it into select with that new bitmap that I computed. That's going to give me the position of the corresponding delimiter of my of the extension that I cared about. And so I just have to scan that extension from right to left until hitting a different delimiter. And yeah, that's the way I basically find these types of delimiters. Does the workflow make sense? More or less? Okay.
Okay, so what is that in the extensions? Looks like the length of each is not different because it's not like the first one has 3.
Right. So each extension the extensions are variable length. They can have different lengths. They're formed of 2-bit fragments, but because there could be a different number of fragments in each extension, I have to somehow resolve how long each one is. That's why I'm using delimiters at the end of each extension. Each delimiter tells me where the extension ends. Okay. So yeah, we have a bunch of other complications here. Of course, as you have more insertions, you may have more and more extensions, and your current extensions may grow. So your extension pool may overflow. What we do is, in this case, we actually repurpose the extension pool as a pointer, and we store that pointer, which is a pointer to an external array of higher order bits. So you can think of these as basically 32-bit integers, standard integers, that store the overflowing bits of every single counter in my chunk. Now, what we do is, well, this is of course a extra memory overhead. So what we do to, counter that is we At runtime, we dynamically tune, based on the workload, the structure of our chunks to minimize memory. So what I mean is we're going to tune the number of counters we're storing per chunk, and we're going to tune also the stub length, so the length of these counters per chunk. That's going to allow us to change the size of the extension pool, and based on that, well, reduce the probability of having these overflowing extension pools, which we have to store pointers for. Okay, so that's going to give us, basically allow us to minimize memory.
So to extension
Yes, we have three parts: the stubs, the extensions, and in the case of an overflow, yes, pretty much. The extension of the extension thing you can think of as, if you're familiar with like front yard, backyard hash tables, you have two hash tables in those structures. The backyard is like super small. It's only used very rarely. The extension of extension thing is we tune the data structure to only have them rarely ever. Okay, so that's how we handle skew. For unbounded streams, it's a bit simpler the way we handle it. So let's say we're applying Sublime to count min sketch again. The idea is to basically expand the number of counters we have in our array as the stream grows. So the way we're going to do that is we're going to look at the stream length continuously, and we're going to expand whenever n hits a threshold. So what this is going to allow us to do is, as the stream grows, we're reducing the probability of hash collisions and therefore reducing the amount of errors that we incur. Okay, so let's say I've inserted a bunch of keys until I've hit the threshold of 4. What I do is I just take the entire array, I duplicate it, and well, this is going to be my new array in some sense. But the core thing here is we're going to use this technique called, it's a very common technique. We're going to use consistent hashing. So in some sense, the hash function we're using in our counter array now is basically a hash function that gives us a really long string of bits, and we only vary the number of bits we take from that long hash. So at the beginning, let's say a key would have hashed to a counter with only a single bit. Now, after an expansion, we take one, where we have an array that is twice as large, we take one more bit of that hash. That's going to allow us to map that key to a different counter. But the nice thing is that new mapping is either going to be to the same counter or it's copied. So the estimation that we're going to get for that key is going to remain consistent over expansions. Okay. So yeah, that's how you do an expansion. Of course, if you get, well, yeah, our policy actually, the default policy is whenever you expand, whenever n increases by 4x, you expand. So this is different from standard data structure policies. Expansion policies where you only expand when n increases by 2x. So we expand by a factor of 2x when n increases by 4x. So if you actually do 4, we can show that the error, well, your array is always going to have something similar to square root n counters in it. And well, if you plug that in, well, this is a bit more complicated than this, but it basically the rough idea is if you plug that square root n into the expected error expression, you're going to get an error of square root n now instead of n. So it's a sublinear error instead of linear errors. Okay. Well, the reason why it's only O of square root n instead of exactly square root n is because, well, exactly square root n is what you would get if you started with an array that was pre-allocated with square root n counters. But here we're increasing the array over time. Now, the reason why we get an asymptotic here is because the old keys that we had are going to be duplicated as we expand. But the number of, so they're going to artificially increase our error over time. But the nice thing is, because there are exponentially fewer of those keys as we expand, the amount of duplication kind of converges, and you get a small constant factor in overhead in the error. Okay, so it's a higher by a small constant factor. So what we achieve is errors that go at a much slower rate in exchange for slightly more memory. This is in some sense the beyond worst case thing that we were trying to achieve, both of these techniques. So the first technique gave us better memory in skewed settings, which is in some sense easier than the uniform case for frequency estimation. And this one, it gives us, better errors when you don't know the stream length. So it's like, yeah, it's a more general setting. All right, and of course, to save memory, we contract the sketch, the counter array, after many deletes. That is a little bit complicated. It's not as straightforward as just like having the array and adding these two things together. But for the interest of time, I'm going to skip over it. Oh, I guess I'm not going to skip over it. Yeah. All right, so again, back to the question of 4x. We actually show in the paper, if you expand when n grows by other factors, you get a wide spectrum of trade-offs. And we basically characterize that trade-off space. In doing so, we actually show that given a fixed accuracy budget, the fixed accuracy we want to achieve, well, we get like an upper bound in terms of memory that we get by just tuning that expansion threshold. We also show a lower bound in our paper, which is basically saying that if you want to design a frequency estimation sketch that doesn't know the length of the stream, yeah, you have to use some amount of memory at the very least. And we also show that this lower bound that we prove is only within a small factor of the upper bound that we achieve with Sublime. So in some sense, this framework that we've come up with is going to allow you to design close to optimal expandable frequency estimation sketches. And you can't really improve on it. So yeah, that is basically it for my talk. Today I spoke about range filtering and frequency estimation. More recently, I've been getting into high dimensional similarity search, which I would love to talk to anyone offline if anyone's interested. And yeah, with that, I thank you guys for listening. No problem. Yes.
Quick one going back to you were talking about the like 1 in 1,000 factor being useful to kind of sit on in CPU cache, essentially.
Yes.
What happens and what are the performance implications of data sets where that 1 in 1,000 scaling either pushes it out of cache or similarly where you have to have a smaller or larger scaling to fit within cache?
Right. So yeah, so when your data set is so large that you exceed the cache size, well, yeah, you're gonna get slowed up, of course, right? We counter that. If you remember, I mentioned that the way we implement this tree is using a Y-fast trie. That trie has a better cache behavior than standard binary search trees. So we kind of like leverage that property to sort of counter this.
I was more just thinking in terms of like the subset selection, in terms of like the implications of that and trying to keep it, because obviously you can engineer your way through to some extent through any kind of tree-like structure and like that to kind of get good properties.
Yes.
But fundamentally, like if the data set is the scale where you're so large that no matter what engineering you do,
it's out of cache.
Shrink it. Do you then what happens if you change to say 0.05 or 0.001 of data size? Like how do the properties you get?
I see the question. I think I understand the question. So of course you can do that. You can like do an extra subsampling over the samples you already have. And basically what you would have to do then is you have to take adjacent infix stores and merge them. This is an operation that you can do because, well, merging is kind of like you're deciding to forget some of the lower order bits that we were storing before. So that's an operation that you can do. The consequences of this is, well, the reason why we're doing sampling in the first place is to basically support more distributions, right? So if you're forced to do more subsampling, you're kind of limiting the number of the class of distributions that you're able to support with this type of structure in exchange for the added benefit of faster searches in cache. Does that make sense?
Yeah, makes sense.
I have a question that for your second part, you consider the frequency of the string, right?
Yep.
This is that you do not use the sliding window search with the model, right?
Yes.
The whole string.
Yes, yes. So the reason why we consider the whole stream is, let me find like a Yeah. The reason why we consider the whole stream is because some applications actually do need to know the entire stream. So for example, if you have, let's say, a database system and you want to implement a query optimizer. In a query optimizer, well, in SQL databases, you do like joins on tables and whatnot. And you have a query planner that has to plan like which joins to do first based on the size of the intermediate joins. So one way people usually do this in practice is they basically store a sketch for every single table, and based on the estimates of the sketch, they determine what the size of that join is. In this setting, well, you basically have to have a sketch over the entire table. You can't just have a sliding window of like the most recently inserted keys into a specific table.
That is so normally do not just store the data.
Yes, yeah, a lot of applications do work in the sliding window setting, but yeah, that even in applications and networks, if you use the sliding window setting, let's say, an attacker can kind of trick your sliding window. If there's like an attacker doing a DDoS attack on your servers and you want to identify that, yeah, an attacker can sort of try to avoid the sliding windows you have as much as possible. So having like an idea of the entire stream is going to be beneficial in that setting as well. That totally makes sense.
What do the attacker can select some very worse sliding window?
So what I'm saying is an attacker can kind of attack multiple servers at a time in your sliding window, but one server is like constant across sliding windows. So that server is like getting hammered over and over again, but because you're using a sliding window, you're not realizing it. If that sort of makes sense. Okay, sorry.
Very weird, but very good. Okay. I don't think there is question on
Navid, just a quick question. So in the Sublime framework for the commits, you have some expansions idea that. So I'm just curious. There might be some constant factor pull up in the error bound, right?
Yes, there is.
Yeah, so you basically you have some kind of geometric errors, right? Every time you expand, and some of the error previously error.
Exactly. Yes, yes.
Okay. Yeah, I think this is a very nice idea. So you truncate the hash value, you still can guarantee a true universal property, and then you still guarantee the error.
Yeah. Thank you so
Very
much.
clever, yeah.
But yeah, you're exactly right. There is some constant factor that we're hiding here. The constant factor itself, to give you perspective, in the case of square root n is like something similar to 4 over 3. So it's super small. And as you sort of bring the expansion threshold closer and closer to 2 instead of some number bigger than 2, that added constant factor converges to something similar to log n. And the lower bound that we prove actually shows that log n is fundamental. You can't do better than the convergence to log n thing.
Okay, interesting. See.
Does that make sense?
Yeah, makes sense. Yeah, yes.
Okay.
Thank you so much, Navid.
Thank you all so much.
Yeah, it's the end of the talk.
Cheers.
Cheers. Thank you.